Okay, now let's start chapter 9. We will talk about some special digital controllers which use the possibility of intelligence in the computer so that we can work on totally different principles if we compare this with a PID controller. We want to start with theoretical, very good controller, but practically really not used. I will tell you this is a deadbeat controller, rather old principle. The name I don't know why this is called deadbeat. This is just an old-fashioned title which is given, I think, 30 years ago. Advantage. Disadvantage. Let's make a short introduction. Advantage. Disadvantage. A list to show you what happens. It is the fastest controller of the world. Fastest controller of the world. Why is this the fastest? Because the settling time in reference step response is m times sampling time. If m is degree of process. This means if I have a first order process like a PT1, settling time is one step, one simple step. If I have a second order system, two PT1s, then I need 2 steps. If I have a 3 PT1 system, 3 steps and so on. Theoretically, there is no faster control mechanism possible, thinkable, and the deadbeat does this few steps. The number of steps is absolutely theoretically the minimum. So it is proven that no controller can be faster than this. Of course, in a PT1, less than 1 step is not possible, but in a second order system, there is no control procedure possible or thinkable which does this in less than 2 steps. So I think this is an interesting theme. So we should work on this principle, learn something about this, and then we can talk about disadvantages, because if you look into the realized controllers, in industrial applications, you cannot really find a deadbeat controller. Why? Because if controller output is limited, Na, was ist denn das hier? Limited. Worse behavior. Then PID. These few steps are only possible if the controller output is not limited and realized with your actuator, and sometimes, of course, this doesn't work. Okay, that's the first. Second disadvantage: if n is 2 or larger than 1. So, what is los heute? Larger or equal to the second controller output is negative big. Negative big. So the question is, in some cases this is not realizable. Negative controller output means in a motor driving system, for example in a cruise control system, this means braking, or in a heating system this means cooling. Yeah, negative controller output sometimes is not realizable. If we have, for example, electric drive, then of course the electric motor can brake, but in a other system, we have a normal gas motor, oil motor, then of course the cruise control system should not influence the brakes. Yeah, so big negative second output sometimes is not realizable, and then you can of course not use deadbeat controller. And the third disadvantage, controller amplitudes are larger than PID. Yeah, your actuator must live with larger amplitudes. Yeah, if you want to be faster, the amplitudes must be larger. So I think that's normal. I think it's also worth to spend at least one lecture with the deadbeat controller, and I will show you what we can do with this, and I will calculate some examples. One step advantage, if process has a delay of d times sampling time, if d is an integer number, then settling time is m plus d times sampling time. So that means if there is a delay of one step, then you need one step more. But in other words, a delay doesn't matter. The controller can work with this delay without any problem. So the design of a deadbeat controller includes process behaviors with a delay, but of course a delay must fit to an integer multiple number of sampling time. That's an advantage. You will see in our real algorithm. See real algorithm. Note there we have a d which is 1. Yeah, then there is a delay. Our real algorithm, the programming kind of a real algorithm, produced one delay, but this can be realized with a deadbeat control algorithm. Okay, let's look how we can design a deadbeat controller. Design C paper, chapter 9, 1, 2, 9, 6. Yeah, in 9.5. Sorry, 9.5. 9.6 is the new chapter. 9.5. Let's look into the content of my paper. If you look into the content list, starting with page 62, you see that here we start with the deadbeat controller. In the preparation, I explained that you need to design the controller. You need the step response invariant filter version. So in 9.2, here you can find for some simple standard blocks the result, the solution of the step response invariant filter version. Then in 9.3, I will present the deadbeat algorithm to design to find out the coefficients of the controller. Then I show you a variant of the deadbeat controller which needs one step more, but has smaller amplitudes. Then in 9.4 you will see that if I have simple blocks like IT1 also, without calculation of the step response invariant filter, you can directly calculate the coefficients of the deadbeat controller. Here for 2PT1, PT1 and IT1, for these 3 blocks you can find in chapter 9.4 direct equations for the coefficients. And then in 9.5 I go through 2 examples where you will see how a deadbeat controller works. Okay, so chapter 9.1, let's go to page 62. Okay, to design a deadbeat controller, the first step, what you have to do is you have to convert your process. You need the transfer function of the process, of course. You need information of the process. In chapter 8 we have talked about identification methods. There we can get with some methods the transfer function of FFP. Then you have to convert this with the equation in chapter 7.2.2 into the step response invariant filter version. This was the mechanism. Take your transfer function, divide by P, look into the Z transform table, take the Z expression, multiply with Z minus 1 over Z, normalize the function, then you have your step response invariant filter function. This is necessary because the deadbeat control design uses the A's and B's of this controller. In 9.2 you see here I have done this job for typical process functions like PT1, IT1, PT2, 2PT1, 3PT1 and 4PT1. For this 1, 2, 3, 4, 5, 6 different process types I have done the job to solve the conversion of your analog coefficients K and T into the A's and B's of the step response invariant filter. Note that this function has coefficients B1, B2 and so on up to Bm in the numerator, and 1 plus A1 z to the power of minus 1 and so on up to am z to the power of minus m in the denominator. So the process coefficients typically are A and B. The controller coefficients are Q and P. So this is a way to avoid mixing up coefficients of a process with coefficients of the controller. We have two blocks. The controller block with P and Q coefficients and the process block with A and B coefficients. So this is a way to avoid mixing up. Okay, M is the model degree. For PT1 we have M1, degree 1, degree 2, degree 2, degree 2, degree 3 and degree 4. So that should be clear. Note that if you have the A's and B's, you can write the algorithm to calculate process output values. The process output here in this case is called Y. Y is a process output, can be calculated with the negative A values multiplied with old outputs plus the B coefficients with the input values. Note that here is no B0. Why is here no B0? Because if I have one of these 6 types, these are all types where the output doesn't jump if the input jumps. That if there is a B0, and there is a step in the input, in the same microsecond, the output changes its values. So because here we have all process blocks which a delay, which inertia, this means there is no B0. And therefore there is a k-1, the first input value here of the coefficients. Okay. Note that these 6 block types can be modeled. If I have these A's and B's, then of course it is easy to use these 6 different types as simulation. In my hardware simulator, I use, of course, exactly these equations. Okay. For example, if we have a PT1 with K and T, this transfer function of an analog PT1, M is 1, that A1 and B1 can be calculated just with these equations. Yeah, if K and T and the sampling time is given, then you can quickly calculate the A1 and B1 with this equation. So never again go into this mechanism for a PT1, because solve for all PT1s in the world. Same as with IT1. If K and T of an IT1 is given, then M is 2, that's a second order system. You have 2 A's and 2 B's with rather more complex equations, but just easily with a computer you can calculate these A's and B's. PT2 the same. This is a standard transfer function of a PT2 second order system, and with the internal new parameters omega and z sub o and delta, you can calculate the 2 A's and 2 B's with these equations. Yeah. We can continue. 2PT1 has 1k, 2 time constants. That is a second order function. Finally, we want to have A1, A2, B1, B2 with internal values D1, D2, D3 and C2, C3. You can easily then go through these equations and follow these equations. Finally, maybe time consuming, but easily solvable. I have done these steps. Here you can find the result also for a 3PT1 system with 1k and 3 time constants. Third order system has 3 B's, B1, B2, B3 and 3 A's, A1, A2, A3. Here you see the equations. You can program it. I have programmed these in my WinDF algorithm, WinDF module. Just the same as with 4PT1, with 4 different time constants, fourth order system, 4 A's up from A1 to A4, 4 B's with internal values B1 with B4 until B4. So I see you can just see it is solvable for any other system. If you need the step response invariant filter function for other type than this, then you have to go through this equation. Okay, so far this is a preparation. Now we have converted the process into the step response invariant filter version, and now I show you how this deadbeat algorithm can be designed. The design step, the mechanism for calculation of the P's and Q out of the A's and P's, is extremely simple. The theory behind it is not so simple. I have a paper from my old colleague, Professor Baumann, who has written the theory how to come to that what we use now in the next step to design a controller. He has described this in a German paper, 5 pages, handwritten pages in German text, but this is just mathematical equations. So I think an American student can also read this text. This document is available in the Lernraum. Yeah, let's write down the simple design rules for a deadbeat controller. The process, process must be described in the step response invariant filter version. We have seen this is a function with b1 z to the power of -1 plus and so on plus bm z to the power of -m divided by 1 plus a1 z to the power of -1 plus and so on plus am z to the power of -m. And let's assume that there is a delay in the process. D must be an integer number. So the process function can have a delay, but this delay must be integer number of the sampling time. Then the controller can be written as fc for the controller of z is a node, a little bit different to that what I have written in my paper, is q0 plus q1 z to the power of -1 plus and so on plus qm z to the power of -m divided by 1 minus, and now I write the general controller design with any delay, minus parenthesis p1 times z to the power of -1 minus d plus p2 z to the power of -2 minus d plus, you see what I write down is pm times z to the power of -m minus d. That is the general algorithm with any integer delay of the process. So the algorithm can easily be adapted if there is a delay in the process. How large are the Q's and P's? That's the rest of the miracle of the deadbeat controller. Q0 can be calculated as 1 divided by sum of all B's. E is 1 to m, bi is 1 divided by b1 plus b2 plus and so on plus bn. Okay, q1 is q0a1, q2 is q0a2, and down to qm is q0 times am. The same is with p1. p1 is q0 times b1. p2 is q0 times b2. You see, the design is just a simple set of equations. And this can be calculated easily with any computer. And you see, we have also a possible adaptive controller, because an identification method can throw out the A's and B's, and with this equation set, you can easily calculate the new set of controller parameters. just some multiplications. Yeah? Note degree of controller is m. That means if I have a first order system, PT1, the controller has also just two Qs and one P, has only the degree 1. If we have a second order system, we have 2 A's and B's, and the controller has two P's and 3 Q's, or time 1 Q more. In the third order system, we have 4 Q's, 3 P's. That means the degree of the controller depends on the degree of the process. This is different. Note the PID always has m is 2. Yeah? There is just constant degree of any controller for any process. If you use a PID, you have just here three multiplications. Here you have more multiplications. So the controller for higher order systems has to need more computation power of your microprocessor. But you see, the design is simple. You can do this before you run your controller or during runtime. That doesn't matter. This controller is called deadbeat controller, and we should do, I think, a first example. But before we do an example, let's have a quick look to our paper. Here you see the deadbeat algorithm has a controller box, a process box. Note I have different indices. Sorry for this. This is the process transfer function. This is the controller transfer function. Here without a delay. Here this is written with a delay 1. I have written this with a delay D. So for any delay. You can convert this transfer function of the controller easily in the algorithm, and then you see you can easily program this controller. If you know the P's and Q's, the controller equation is just one line in C or C#. And here you can find exactly that what I've written. Q0 is 1 divided by the sum of the B's, and the Q's and P's depending on the Q0 and the A's and B's. So this is just very simple, and I think we should do simple example with the PT1 in the next video.